Hello, everyone. My name is Jason Dillerman. I am the current tech lead for the Rados block device portion of Ceph. Um, the goal of this talk today is to walk through the I/O path of how read and write requests get translated from the LibRBD API down into calls to the OSDs and back to the user of the API. I guess to start, I am going to share my screen. Can everyone see my screen? Yea or nay? Yep. All right. That's 1+1. All right. So I'll count that as it's working. As I get going, since I won't have the chat window visible, if anyone has any comments, questions, I'll stop from time to time and ask if anyone has any comments or questions that I can try to answer in line. Otherwise, if I forget and I don't, feel free to speak up and chime in so we don't get too far ahead. Just to start, though, I did want to touch briefly on the high level of how data is organized for RBD. And so when you think about a block device, you have you can almost think about it as a flat file from byte 0 through byte whatever. Let's say it's a 1 terabyte block image. You're going to have, you're going to be able to address all the bytes between byte 0 and byte at 1 terabyte. But the way that is internally represented and stored within Ceph is that RBD, be it KRBD or libRBD, KRBD is in the kernel, libRBD is the user space tool library. What it does is they both break down those requests into much smaller, much more manageable backing objects in the Ceph storage cluster. So all this is documented here on docs.ceph.com. If you go to the architecture section, there's a link on how data striping works. So regardless of the size of the image, RBD only talks to backing Ceph objects that are of a fixed size. The default fixed size is 4 megabytes. So if you just do from the RBD CLI, you do an RBD create -- size 1T and then an image name to create a 1 terabyte image. You're going to have it's going to use the default 4 megabytes backing object size when you first start writing data to that image. And it's RBD, everything is thin provisioned, so there's actually no data besides a little bit of that metadata describing your image when you first create the image. It's only as you start writing data to the image that backing data actually starts getting written to the OSDs. That is, unless you use the -- thick option when creating, and in which case it actually will thickly provision your image and make sure that every image or every backing object of the image is fully allocated. But getting back to the striping, you can just think of it as very simple RAID-like striping. The default case is that it has a stripe unit of the object size. So if the object size is 4 megabytes, the stripe unit is 4 megabytes, and then the stripe count is 1. So in that case, bytes 0 through 4 megabytes of the object go into object 0, bytes 4 megabytes, 8 megabyte go into object 1, and so on and so forth. If we look at this RBD types.h file for the new, and I say new loosely because it's been the default for a while now, but the RBD image format too. And the way that those backing data objects are then represented in Ceph is that you have these just these objects called prefixed with RBD underscore data dot, and then it's got the unique image ID, which is generated when the image is created, and then it has a sequence of like an index into the image. So for the simple case of just a 4 megabyte object size stripe count of 1, then you can just take that index and multiply it by 4 megabyte the object size, and that's how you know which object to go read and write to when it comes to getting your data. Any questions so far at the high level about how RBD breaks up data? Okay. Um, so as I mentioned, what this talk is about LibRBD. This is a user space library that different programs can compile and link against to utilize and access RBD images. I think probably one of the most well-known integrations is going to be QEMU. Here I just have the the QEMU source code. And in the block subdirectory, there's this rbd.c. This is the driver for how QEMU interacts with librd. But it has its own internal hooks about how to do reads and writes and flushes and all that. All QEMU then has to do is swap its internal API calls into librd API calls. It just so happens that it always uses the same helper function method, which is this rbd underscore start underscore AIO. It determines if it's old enough, if it's a way old version of librd, so it needs to use a bounce buffer. If so, it has to copy all the IO into because it might be an IO vec, has to copy the IO into a bounce buffer before issuing the read or write. But if it's a new enough version, it just can pass that data right to librd. So in this case, you have librd calls for AIO write vector, or read vector, or flush, or discard, and so on and so forth. So at a high level, that is somebody that's trying to use RBD. That's how they translate their IO requests into librd. So those APIs then, we provide those APIs in both the C, C++, and Python bindings. The Python bindings are actually just a thin wrapper around the actual C API, so it's not a native Python binding. So when it comes to the C API bindings, that's what QEMU uses because that's what QEMU is built in. But if I search for one of these calls, we have both synchronous blocking IO methods that kind of correlate hopefully closely to how POSIX standard IO methods would be with read write. And we have AIO equivalents, which would be non-blocking, and you provided a callback that you're going to want to get invoked when the IO is complete. All these methods in the C API, they take this RBD image type T. That is something you get when you invoke the RBD open command. You give it a Rados IO context, which basically is a connection to the cluster and a specific reference to a specific pool in the cluster. Let's say the RBD pool. You give it the image name, and then it'll do all its magic on the inside and populate this RBD image T such that all the remainder of the image-specific API calls are good to go. On the C++ side, it's similar, except everything is kind of wrapped in objects. So in this case, we have an image object that has various methods on it, like reading and writing, and the AIO equivalents of all those methods as well. And then the Python bindings, again, are very similar with, the various reading, writing, and the AIO equivalent methods of how to do IO against the image. So before I then dive into the actual behind the scenes of how these API methods work, any questions so far on the API? Okay. Well, so the APIs are defined if you're in the Ceph source tree, Ceph source, and then include RBD. There's the C version, the C++ version, and the Python bindings are in a pybind subdirectory instead of the include directory under an RBD subdirectory. But LibRBD specifically, it is located in Ceph source LibRBD. It's pretty much self-contained from there. We try to break down all the various internal subcomponents of what LibRBD can do into different classes and namespaces. Namespaces would be in their own subdirectory underneath the main LibRBD subdirectory. But in terms of where the API methods first hit, it's in this file called librbd.cc. So this is just a giant translation file that is it keeps the ABI the stable for the API, so that no matter what version of librbd shared library you're running against, with dynamically linked against. Hopefully, the goal is it didn't matter what you compiled against, because this librbd.cc file is what's responsible for maintaining that API's binary interface. And what it will eventually do is, if I go and find one of the API methods like read, like image read, all it does is it translates any of the data coming in and invokes now an internal non-stable API method for handling the actual I/O. In the C++ side of the house, because this is the C++ version of a read call, we don't have to do much translation because everything is already kind of handled for us. But in the or just RBD read. In the C world, we're given just straight up buffers, pointers to the locations in memory and lengths. So we have to kind of translate some of those, around some of those things. Instead of using the C++ buffer lists, we natively kind of wrap that around with little helper functions to represent that buffer and length in memory to say where we're going to store the read result, or in the case of a write, we actually have to we kind of translate and copy. We have to copy the memory from a C buffer into our internal buffer list implementation, which is what you see actually happening here, where it's taking the buffer, the raw pointer buffers you're providing, and it's creating just a buffer list that points to that data for use internally. So this is just the API translation layer, but the next layer it gets into is where we actually then start implementing how these IOs are going to get broken down for getting sent where they need to go. So we're starting, the historical trend of libRBD is that all the internal non-ABI locked functions used to be in this file called internal.cc, which grew to a giant, thousands and thousands and thousands of line file, which was hard to maintain. So the goal that we've been moving forward with release to release to release is anytime we have to do any major work on a given function, we actually try to break it out into its own API / XYZ. In this case, all the IO functions have been broken out into an API / IO namespace, where then we handle all the internals of what we need to do. So the first set of IO methods that are up here, they're all the synchronous versions. So blocking reads, blocking writes, blocking discard calls. But what we kind of do under the scenes is we just actually translate all those synchronous calls to asynchronous calls, and then we just wait for the asynchronous completion to complete before we move on. So there's really not much to any of these blocking synchronous calls because they really just call the AIO version of this of the same method, which all those start down here with the AIO underscore prefix. So yeah, when we get a request in, it comes with a completion callback. So this AIO completion object holds enough state information that when the IO has completed, we know which, we have a pointer back to a function that the user provided so that we can call it back, or if the user didn't provide a callback function because they're going to do something like polling or something like that, we can at least mark the AIO completion as complete. So when the user that's using the LibRBD API next checks the AIO completion object, it's marked as complete, and they know that it's ready for use. But the calls like the AO read, AO write, they have an offset and a length. This offset it's in image space, so we think about like an LBA address or something like that on a hard disk. It's representing the absolute position of the byte within the RBD image. So this is before we start translating it down into the internal object-based and object extent style IOs that actually get translated to the Ceph cluster. So at the API layer, at this point, everything is image extent based IOs. We have some boilerplate code that's been in here. I don't think it's actually ever been used besides by some testing groups where there was this goal to be able to trace all IOs flowing through the system from the front end of a LibRBD API all the way to the OSDs, to the replication, across the OSDs and back. You could get a complete picture of how a single IO moved through the system. So I don't think anyone ever turns this on, but that's some boilerplate code for that legacy functionality for tracing. First step we come in through, we kind of initialize the completion. We basically say, hey, we started the IO at this time, and that's how we can start tracking latency statistics later on once the IO completes. There's an alternative. As I mentioned, you can provide the AIO completion a callback function, or you can do a polling loop. This is so if you have marked your image as saying you're going to use an event socket to get notified on instead of having a callback function, this just is a way that we internally do some bookkeeping on the AIO completion to say, hey, you're not going to do a callback. You're going to do you're going to notify the event socket to say, hey, there's data or completions that are available for polling. We do some trivial IO validations before we actually issue it, and then we translate the read request, in this case, into this little helper object that just represents that IO request, and this is what helps keep track of our IO state as we move through different dispatching layers, and I'll get into that shortly. But you can just think of this image dispatch spec as it just has enough data just to describe a given IO. In this case, a read IO. But if you go through it, it's the same pattern over and over again. Here's an image dispatch spec that describes a write or a discard or a write same operation. A write same operation is when you just give a small buffer and you say, hey, write that same buffer over and over and over again X number of times. In this case, a write zero call. This one's a little bit more complicated. I can get into that at the end, but it's a way to translate between. It's a way to ensure that your data is actually zeroed out, because a discard is not guaranteed to always discard and zero out your data if the discard alignments don't properly line up with Ceph expectations and alignments. Compare and write operation that just says you give it a buffer to say, I expect the data to look like this on the disk, and then if it does, then you can override it with the data I give you. If it doesn't, throw an error and give me the offset at which the data mismatches, and then a flush operation, which just ensures that any writes that you had provided have actually been persistently written to the backing OSD before completing the flush. So now we've taken an IO from the front API layer, we've translated it to the internal API layer, which now starts the process of pushing the data through our internal IO dispatching engine. So the first thing we saw was that basically every single IO in the system gets translated into this image dispatch spec, which just describes the IO. And it has enough data to store, if it's going to be a read, a discard, a write, write same, compare and write. And then it stores it in a giant, effectively giant union, so that this data structure, only stores the data, doesn't store, the size of the size of the structure is, the size of the largest substructure. And then we store some additional metadata that we need for, in terms of, well, here's the completion that's associated with the IO, the image requests, the extents, with the image extents are, what are the offset and lengths, and you can have more than one internally. The tracing information and so on and so forth. And the other piece of data that it stores is this image dispatch layer. And as we talk about this next, is when you send this request and issue this request, the way current LibRBD works is that we now, instead of hard coding a bunch of if then else statements throughout the code for handling how we can interact with different plugins, we now have a way where we can dynamically and programmatically just take an IO and iterate it through different hooks to let different hooks manipulate the IO as they want to. And those hooks are defined here as an enum. I'm in the IO subdirectory, IO namespace, and there's a types folder, and here's just an enum that describes some of the various dispatches layers we have for manipulating and doing things with incoming image-based IO. So first one we have is, the first real layer that we have is this queuing layer. All it does is it takes your IO, puts it on a work queue, and then basically returns the control back to your calling application. Because when you think about it, if I'm QEMU calling in to my API function, it's not until it hits this queuing layer then it completes control and returns control back from, this, let's say, AIO write call from QEMU. So all that does is it throws it in a work queue to say, hey, there's another thread, a LibRBD thread that's eventually going to handle the IO. It's going to pop things off the queue and issue the IOs. We have a quality of service layer that handles throttling. So anytime you define throttling parameters to say, like, a given image is only allowed to utilize, 100 IOPS, that's handled by the QoS layer. The exclusive lock layer, it's just a hook that says anytime it sees a write operation in, it makes sure that the exclusive lock is actually acquired for the image. And if it's not acquired for the image, it attempts to acquire the exclusive lock. So it handles all the interactions with acquiring the exclusive lock when the first IO comes in. Or if you lost the exclusive lock, reacquiring the exclusive lock as IOs are issued. The refresh layer, we have this notion that we have the, on these new style RBD images, we have the RBD header object. So it's RBD_header dot, and then your unique image ID. That header has a potential lot of metadata on it, like it includes metadata about the image size, snapshots, things like that. So those are things that can dynamically update while QEMU is running. So I could have an RBD CLI process on node A manipulate an image, but that image is currently being used on node B by a keying process, we need some way to instruct that RBD uh, client on node B that, hey, some data has changed about the image. You have to go refresh the metadata about the image so that you know about, a new snapshot or that the image has been expanded or so on and so forth. So the refresh layer is responsible for detecting those changes and then issuing an asynchronous call to go refresh the image in the background. And it pauses the I/O while that refresh is occurring. The next layer is a new layer for the Pacific release, and this is the image migration layer. This is in support of instant image restoration from a read-only source. So I could have an RBD image that's on an S3 endpoint, and I could use the RBD CLI to define a new image to say, hey, the parent of this image is actually, on this remote, HTTP S3 protocol endpoint. Whenever this clone effectively doesn't have the data, go get the data from this external endpoint. So that migration layer is what actually takes care of translating, IOs into whatever formats data might be stored on. That is because it's probably not going to be stored realistically in the native Ceph format. Journaling layer. This is for RBD journaling features. There's a write blocking layer. This is just used for internal metadata. Whenever, let's say, we create a snapshot or something like that, we need to basically pause I/O while that snapshot is being created. We can use that write block layer to basically block all writes from occurring while we're doing this internal bookkeeping, and then we can resume all writes. Write back cache layer. This is related to Intel's work with a persistent write back cache. That would be a local cache that writes to an SSD or an Optane device on your local node. So to hopefully the goal is to reduce tail latencies on writes. And then finally the next layer is the core layer, and that's actually what sends. If the I/O gets all the way to the core layer, that's actually what will send the I/Os on the next step to get them ready to go to the Ceph OSD cluster. So any questions so far on the image I/O, image extent I/O? Okay. All these layers, they're pretty easy to find if you want to dive into depth for the different layers. They're all basically stored as their own file. So here's the queue image dispatch layer. Here's the quality of service image dispatch layer. Here's the write blocker. So they're all pretty easy to find. They're hopefully well named. But the one I want to focus on next is the core one, the core layer, and that's what starts the process of doing that striping operation to determine, hey, I'm talking about image extent 4 megabyte off through 8 megabyte. That means that I'm actually going to send this I/O to object 1 in the backend cluster, and that it's using object extents, 0 bytes through 4 megabytes, because that's just the way the rate translation works. If you go look back at that cheat sheet on the data layout. So the core layer is in this image dispatch. This is the core layer. All it really does is it's just a proxy translation layer between this newer style pluggable I/O handling engine and the original legacy I/O state machine, which is this image request class. So the dispatch layer will invoke the appropriate method on the API, be it a read, a write, discard, write same, compare and write, flush, you name it. But here in the image dispatch class, it's going to translate it to the associated state machine class in the image request. So if I pull up the image requests, it has a bunch of helper methods, which are just those AO read, write, discard, flush, write, same, and compare and write. These are all legacy functions. They've been around for a while, so that's why they're being used by the dispatch layer. But really, all those functions is that they're just factory methods. Because what happens is, at the end of the day, each of those methods instantiates a very particular kind of object, be it an image read request, an image write request, image discard request, and then it just invokes the send method on those objects to actually kick off the state machine. It's unfortunate, and I'm apologizing in advance, but we try to do a good job, at least on all our modern state machines, that we actually have a little ASCII drawing to describe the state transitions and between the state machines. Unfortunately, because this is so old, it's one of the original functions. It's just been tweaked and tweaked and tweaked as the years has gone on. It doesn't have the ASCII drawing that makes it a little more clear as to how the state machine transitions between the different functions, but we can just dive into it. So if we look at the image read request state machine, you first saw actually that everything invoked a send method. Read, so it instantiates the object and calls a send method. That send method is the same virtual method on every single class, which is in the base class, which is the image request. So all that send method does is it optionally kicks off a little side state machine that will update the timestamp on the image. So if you ever do an RBD info command on recent versions of, or at least semi-recent versions of RBD, you'll see a create date, and an update date, and an access date. So this is how those timestamps, the modified timestamp and the access timestamp are updated. Is that there's a little side state machine that says, based on your image property, that says I'm going to update my modified time or my access timestamp every 20 seconds, or whatever your settings are, because it doesn't update it with every I/O. It just does it on a periodic interval as your I/O comes in. So if that period of time has come up, it'll kick off the state machine to basically update the timestamp, which is just sending off this I/O request to that RBD_header.unique image ID object to track the access or modified timestamp. But that doesn't really affect your I/O flow. That's just something that gets kicked off, and that's actually running concurrently then with your I/O. So the next thing that actually happens is it calls this pure virtual send request method, and that's where each type of I/O has its own breakdown from that. So the reads versus the writes have their own send request method. For the read, first step it does, it says, well, if you're using RBD, the internal RBD cache, and you haven't said that you're doing random I/O and you have read ahead enabled, it just optionally kicks off another state machine that says, hey, analyze this I/O pattern and see if someone's attempting to do a bunch of sequential I/O, and if they are, in the background, and also asynchronously to whatever this user is requesting, start reading ahead of the user and filling up the read cache so that future I/Os might be satisfied by the read cache. The next step is, this is still an image extent based I/O operation, so we need to then map all those image extent I/Os. If I'm reading the block device at offset 4 megabytes, that actually is going to translate to a very specific RBD backing object for this image. So that's what this mapping does. It's this little helper striper function that does all the calculations to say, given these image extents, map them into one or more object extents. because if we go back to the picture for how striping might look, I mean, striping might get complicated, and it might be that my image extent has to go across, multiple objects multiple times potentially, and include multiple extents of multiple objects as it loops through. I might have to read stripe unit 0, 1, 2, 3, 4, 5, which means I'm reading from two sections from object 0, two sections from object 1, one section from object 2, and one section from object 3. And when all that reading completes, I need to be able to reassemble all that data appropriately so it goes back in the correct order that the user actually expects it in, because the user shouldn't have to know about, the internal details of how RBD is striping its images in its design. So that's all this function does right here, this file to extents. It maps image extents file to object extents, in this case extents. The naming is kind of legacy and leftover from Cephfs and the original Cephfs client, so that's why the method name is called file to extents and not like image extents to object extents. Because it's from a point of view of Ceph, but it's the same math for both. And we also keep track of this buffer offsets. It also is, as it's doing these mappings, it's also keeping track of when it has to reassemble this data, all the stripe data. It needs to know where to go put that data back into the buffer that the user has provided, so that the data is in the right order. So now we have a bunch of this file to extents is populating this object extents collection. So now we actually can get started with the read request, which is we give the AO completion. We had stored the read result in it, and we also basically tell the read result, hey, when you have to reassemble it, here's the original image extents of how everything gets reassembled. There's a couple different permutations that actually need those image extents. Some of them don't need it at all, so this is a no-op function. We can dig into that later. But we actually issue the request, so this AO completion, we can tell it, hey, you're going to expect object extent count number of requests that are actually going to be issued concurrently, so you have to wait for this many internal requests to complete before the actual user side AO completion is actually complete. And then it iterates through all the object extents, and it issues. It's a very similar pattern here. So now instead of an image dispatch spec, it's actually going to issue these object dispatch specs, and it's very similar. It describes it as a read, it describes it as a write, it describes it as a discard, depending on whatever state machine you're in. So this is the process now to start kicking off a read. We go to this write side, most of it's the same. So there's between the different write methods, write, a discard, a write same, and a compare and write. So most of the methods actually get kicked off from this generic send request method, but it's very similar. It does the same computations of converting image extents to object extents. It does some extra work about pruning, which is basically saying if the write goes beyond the object boundaries and things like that, then we will truncate those IOs so that we're not going past the end of the image. But then the same thing, we set the number of requests that we expect, and then the one place we start differing here is if the journaling mode is enabled, and this is still legacy code because the journaling hasn't been broken out into its own dispatch layer yet. But when it does, this will all be the read and write methods will basically look exactly the same. But right now, we have this special hook that was, like I said, legacy. Where if you had the journaling feature enabled, we kick off a journal append that describes your IO, which gives us a unique journal ID that we can then use that journal ID later on in the object request. And I say that we use it because we kick off the journal append requests, and we also still proceed with the sending of the object request with one exception, because if the data can just hit the cache and stay in the cache, it's allowed to stay in the cache. And but once once the data is actually trying to get written back, that's when the journal ID is actually used, because we actually stall and prevent any writebacks from happening until we are sure that the journal event has been properly committed to disk. So this was just a little speed up way that if you had write-back cache enabled, that your I/O would appear to complete faster, but it's really just being held in memory while the journal event is being appended. And then once the journal event is securely written to disk, then we're allowed, that write-back is allowed to proceed. But the send object request, if we go look at this, there's going to be a different send object request for each thing, where it iterates over the extents, and then it calls a pure virtual create object request, which creates an object request, and then it sends it. So the different methods create different objects. So here's a write request creating object request. So it just creates an image dispatch object dispatch spec create write. You'll see the same thing for here is a discard request. All it's doing is creating a discard object dispatch spec. Write same thing. Compare and write, same thing. So any questions on, so the next section I'm going to talk about is object I/O dispatching, but any questions on image extent dispatching and how the I/O now has gotten broken up into object I/O extents? These are the I/O ranges within individual objects. So it's going to identify the I/O saying this belongs to object 0, and I want to read extents of that object of bytes 0 through 4 megabytes. Any questions? All right, well, the object dispatch spec is actually very similar in design and function to the image dispatch spec. It just has to store a little bit different data. Specifically, the most important piece of data it needs to store is the object number in which that I/O is going to get issued against. But other than that, it's very similar. It's offsets and lengths and various other properties. So it's same concept, where we store it in a giant, essentially union, all the possible different I/O types. We store the current layer in which this particular I/O is currently processing on. We store a callback so that we know how to basically complete the I/O to basically then hooks back into the AO completion to finish off the AO completion. If we go look at the types again, the object dispatch layer types, we have a caching layer. So this is the legacy LibRBD in-memory cache. Those work on the object level. This is different than the Intel persistent write log write back cache. So this is an in-memory only cache, write back or write around or write through. We have a new crypto layer cache layer that's coming in with Pacific, where we can internally have, let's say Lux encryption on an RBD device, and LibRBD handles all the encryption internally. So this crypto layer is actually going to handle block alignments and encrypting and decrypting IOs as they come in. We have a journal layer that's responsible for blocking IOs that haven't committed to the journal yet, based on that journal TID. We have a parent cache. This is something that came in Octopus. This is if I have a cloned image of a parent, all the data of the parent is read-only. So the parent cache is it talks via domain socket to this daemon called the Ceph mutable object cache daemon, which is responsible for basically promoting hot read-only objects to a fast local cache on your device, so it can serve reads locally instead of sending the reads and redirecting the reads back to the Ceph cluster. So if you had a lot of golden images or something like that in RBD, in theory, that's what the parent cache could help you with. There's also work, I think, being done to incorporate it into RGW for immutable objects in RGW. Next layer is a scheduler layer. All this does is it tries to determine if you have a bunch of sequential IOs. So this is just a very dumb IO scheduler. It says it looks like you're doing a bunch of sequential IOs to a given object, so it'll try to collapse all those sequential IOs into a single IO request to the backing OSD, because that's going to be faster and more efficient for the OSD to do than it would be to send it dozens of individual small requests. And then finally, it gets down to the core layer, and again, that's the layer that finally sends the IOs to the backing Ceph cluster. So similar to how it's easy to find hopefully easy to find the object dispatch layers, hopefully it's also easy to find it's easy to find the image dispatch layers. It's also hopefully find the object dispatch layers. Like here's the scheduler dispatch layer. The initial implementation we just called simple because it really is doesn't try to do anything fancy. It's just trying to do detect sequential IOs and batch them up. So that's a simple scheduler. And then the core layer comes down to just the object dispatch. And so it looks very similar to the image dispatch. All it does, it's kind of a translation layer between the old world and the new world. The old world being this object read request or discard request or write request state machines, and the new world being this pluggable dispatch layer. So it just translates between this API and the original legacy LibRBD API. So as the different methods are invoked by the dispatcher, be it if it's an object dispatch spec that's describing a read, it's going to invoke the read method. If it's a discard, it'll invoke the discard. If it's a write, it'll invoke the write method. They all get broken down into the appropriate state machines that are all described. And these are the core state machines that actually then perform the IOs against the cluster. And these ones actually do start to have some ASCII drawings in them. So it's very similar as before. We have the factory methods. They don't do anything except instantiate state machine objects. State machine objects are what then send you through the state machine, be it a read request, an abstract write request. We call it abstract because there's different kinds of writes, be it a true I'm writing data versus I'm discarding versus I'm doing a write same or compare and write. Those all just are slight tweaks on the concept of the abstract write state machine. But if we go look at let's say the first one, the read request, it gets entered in with the send. So the first state is it's going to go and just issue an object read request to the cluster. So it determines, first step, it determines what you're trying to read, be it if you're trying to read the head of the image or a given snapshot of the image. If you're happy to read the head of the image, like you're not trying to read from a snapshot, that means that we can then go check the object map and things like that, because the object map will be in memory. So we can go check to see, hey, does the object map say if we know that the object may or may not exist? If the object map says there's no possible way for that object to exist, we can actually just skip ahead, and we don't have to issue that initial read request to the OSDs. Otherwise, what we do is we, for all the extents, the object-based extents, so this is like read bytes X through Y in the object, and we can have more than one extent that we're going to read, we can issue either a sparse read to the OSD or a read to the OSD. And we just have like a little hint here that says, based on this configuration setting, which is, I think, defaults to like 64 kilobytes in the config. So if your read request is greater than 64 kilobytes, it tells the OSD, hey, try to do a sparse read for me, because what a sparse read does is it won't return blank sections of the object. So if there's no data there, it'll return, no data. It'll say, hey, the data I gave you back really only represents extents from point A to point B and from point C to point D, and there's a gap somewhere in there, and it's up to you to do the math to figure it out. But it doesn't inject a bunch of zeros in there where there weren't any zeros before. It keeps the data thin. And then we just execute the method on using the LibRados API. And when the data, this is an asynchronous method. This is non-blocking, so this goes away, and eventually once LibRBD comes back with an answer, it's going to invoke its completion callback, which is the handle read object. And we get told by the OSD the object doesn't exist, in which case we may have to go read from the parent if it's a cloned object. Otherwise, if it truly is an error, we have to, we'll bubble that error up to the user. Otherwise, no errors, good to go. Then this request is done, and what this finish thing does is it goes and tells the original AO completion that this particular request is complete, and the AO completion that's tracking all in-flight requests. Once it gets down to 0 in-flight requests, will finish itself off. But if we need to read from the parent, and minus this little special flag that you could pass to the state machine that says, hey, do not attempt to read from the parent. In 99.99% of the cases, it is going to read from the parent, in which case we just invoke this little helper method here that if we go look at in utils, read parent, I pull up the H file. I think I'm going insane. Parent. There it is. All right. This is missing. So all this is just a helper method because we had a few places in code that were doing the exact same logic over and over again. So we got broken out into a helper method because when you want to read from your parents, from your parent image, you already had an IO that's coming from a given object. Let's say object 1. Object 1 might represent actual image extents, 4 megabytes through 8 megabytes. So we have to translate these object extents back into image extents. So we're kind of reverse mapping those object extents back into the parent image. So that's what this method does. It's just the reverse of mapping an image extent into an object extent. This maps an object extent back into an image extent. And then once we have these parent image extents, we determine if we have an overlap with the parent because the parent might be smaller than the current child because you expanded the child. And then we would potentially prune those image requests based on that overlap. And assuming we actually have data to read, because there actually is an overlap with the parent for that given read request, then really all we do again is just issue another. We start a brand new AO completion for tracking a read, and we kick off a new read request. But instead of issuing the read to ourselves, if this image context represents us, this image context parent actually is another image context that is all the state about the parent. So it just issues the read directly to the parent image. Going back to if you read the parent, same thing. Checks for errors. If the parent didn't exist, that means there's no data to read. If there's an error, bubble the error up. And then we optionally there's this field, which I don't think anyone ever uses, but you can enable copy on read or copy up on read. So if you had to turn that on an image, what's going to happen is if you issued a read request that the object doesn't exist on the child, but it exists on the parent, then it's going to actually then kick off this little asynchronous state machine in the background to go copy that parent data up from the parent image to the child image so that you stop having to go read the data from the parent in the future. And that's all that. This is just boilerplate for handling that case of kicking off that asynchronous requests, kicks it off, it forgets about it, and moves on and finishes the read request. But in terms of writes, just noticing that we only have a little time left. I just want to point out it does very similar things. It checks to see if the objects may exist, if there's any optimizations it can do. It potentially updates the object map because again, this is legacy code before we broke anything out into layers in the future, I would have said this was object map would have been its own layer. And then assuming everything's good to go, it kicks off the actual write requests. And again, if there was a copy up, it can, if it's a child or a clone, it can put an assertion on it to say, hey, you're not allowed to write this unless I know this object already exists on the child image. Otherwise, it's going to, give it a write hint, add some write ops, and execute the Rados API call. And then once it's done, it gets invoked back down into handle. In which case, if the object didn't exist, which that really only way to get that error would be if the pool didn't exist, or if we had that assertion exists firing, that means we actually have to perform a copy up, which is complicated. We don't have enough time to do it at this point in time. Otherwise, the write should be complete. The illegal sequence is related to compare and write. That's an expected error from compare and write if you had a bad data. It completes, and then it potentially does a post update of the object map, which only happens with the discard, because you might remove an object, because the first state to update it would be to mark it as removing pending, and then finally you go and remove, mark it as non-existent. And I'm sorry we're running out of time. Maybe we'll schedule another talk about this to dive more into it. But in the couple minutes left, is there any other comments, questions?
Maybe this could be for next time, but it might be interesting to see how you test all this in the unit test as well.
Definitely, yeah. We have quite the extensive unit test library. Definitely way more code in unit test than we have in actual LibRBD code, which is great. It gives us hopefully good confidence that the code we're putting out there is going to continue to function. We don't just have to rely on high-level integration tests. We actually can get down into all these classes and test them individually. Anything else? Well, I'm sorry that we ran out of time. I was hoping to get a little bit further. But yeah, like I said, we can definitely schedule another one of these to dive in again. And yeah, I guess thank you all for joining, and you can reach me on the mailing list any number of ways if you have any other questions that you don't want to raise here, but you want to still have lingering in the back of your head.
All right. Thanks a lot, Jason.
Thanks, Jason.
Thanks all.
See ya.